My first question is how to check this one is convergent or divergent. Right? Think about that. Yeah, n starts from 2, because if n starts from 1, the denominator is going to be 0 the first term. Right? Yeah. That's my first question. Think about. I'll give you 1 minute to think about. Okay. If it's convergent, prove it. If it's divergent, prove it. Okay. At least you share some have ideas how to do that. Okay. First of all, let's make a conjecture. This is a convergent. So reason is you know the minus 1, you get 1 over n squared. That's n squared is the dominant, the term dominates the rest of it. So by the P series test, it's convergent, right? P is going to be 2 is greater than 1. Okay, but you cannot say that directly. Just that's not a proof, because this series you can only say it's above the 1 over n squared. Okay, but not exactly. Before we study the comparison test, I have 2 different ways to prove this is a convergent. Okay. The first method, direct proof. Okay. Direct proof is I just want to look at the partial sum. All right? If this one has a limit, then it's convergent. Maybe even you can find the limit. How do we know this has a limit, right? So let's try. I'm not sure yet. Okay, so let's try. So 1 over n squared is going to be n times minus 1 n plus 1. Okay, you can decompose it. It's going to be n minus 1 minus n plus 1, but you have to divide by 2. Yeah, just view this like an x, right? X minus 1, x plus 1. You can express like a over x minus 1 plus b over x minus plus 1. Then you can determine the coefficient. But you can quickly see that n cancels out in the denominator. You get 2, 1 plus 1 is going to be 2. So divide by 2. Okay. So if you recognize this, what I'm going to do is I'm going to look at, you see, this is a, right? First of all, you will have when n equals 2 is 2, sorry, how many terms you're going to get? Yes. I'm not sure how we can cancel it now, okay? Let's try. So when n equals 2, that's 1, 2 plus 1, 3, plus 2 times 4, plus 3 times 5, plus 4 times 6, and so on, right? And then the last term is when m equals n minus 1, so n minus 2, n minus 1, so it's m. Okay, so those are the terms. Now let's separate them. Are we going to cancel all the terms? I think maybe we can. So let's look at the 1/2 is there, take it out. So 1 over 1 minus 1, 3, 2 minus 1 over 4, plus 3 minus 1 over 5, and keep it going, right? Okay. If we don't know how to cancel all the terms, because we just put the positive terms put together. The positive terms is 1 over 1 plus 1 over 2, 1 over 3, 1 over 4, right? And keep going. The last term is 1 over n minus 1. Minus is a negative term. So 1 over 3, 1 over 4, right? Begin with 1 over 3, 1 over 5. And 1 over m plus 1 over m plus 1. Okay, then there are lots of terms in common. Okay, how to do that? I think this is a n minus 1, right? So this part can be canceled out. And from here to here, right? So you will get 1 over 1 plus 1 over 2 minus 1 over 3, no 3, 1 over m plus 1 over m plus 1. Okay, clearly it approaches, okay, which is going to be 3 over 4. So we find it. So we not only prove the convergence, we also find the sum. Got it? Just use the origin definition. Okay, sometimes you can do that. Okay. Right? Just a partial sum, you can cancel out the terms. So in general, if we have an n plus n minus a, for example, and n plus b, and this is going to be n minus a minus n plus b. But when you do subtraction, n plus b minus n minus a, so a plus b. So you have a plus b canceled out. This is identity. Okay. Now, what else we can look at? We go back to this, right? We go back to this. And the n is 1 over n squared minus 1, right? So this can be written as f of n. What is f of x? F of x is 1 over x squared minus 1. Clearly, it's on the interval from 2 to infinity, right? I think, first of all, this is a positive. Second, it's decreasing, right? Obvious, because nothing is a numerator. Denominator is getting larger and larger. Denominator increasing the whole fraction. So we can use a integral test, okay? If we are able to evaluate the integral, right? Because if that meets these two conditions are satisfied, then you can apply the integral test, right? Then you look at the integral of this, and it's convergent, but you can even evaluate, find the value, okay? We can find the value, okay? How to do that? Again, you do the same decomposition, okay? So x squared, right? Scale, if you get a over b, right? A x minus 1, b x plus 1, then blah, blah, blah. Finally, you still get 1/2. Okay, you will get this. Okay. Then the antiderivative of this function would be 1/2 natural log x minus 1 minus natural log x plus 1, right? Plus constant. So you can simply express it x minus 1 over x plus 1 plus constant. So this is the antiderivative of the function. Then evaluate the integral from 2 to b x squared minus 1 dx, right? Is going to be the difference b minus 1b plus 1 minus 1/2 natural log 2 minus 1 2 plus 1. All right. Clearly it has a limit, right? Because this fraction approaches 1. So this approach, if b approaches infinity, it's 1/2 natural log 1 minus 1/2 natural log 1 over 3. So the answer is negative when, but this can be also written as it's a positive number, okay? Because natural log 1/3 is negative natural log 3. So it's a finite. So that means, hey, that means that implies it's convergent. That implies is convergent. Okay, since the integral is convergent. Okay, and by the integral test. Okay, by the integral test. Okay, let's stop here. All right, so the idea is that you define the function f of x. You verify the condition supposed satisfied by the function for the integral test. Then you say I can use the integral test. Then you evaluate the integral, and to evaluate the integral, you have so many techniques, so that you know that, right? So assume that you are able to evaluate the integral. Sometimes you cannot, not always, okay? Sometimes you cannot evaluate the integral, so you have to give up. That's what we work in the learn comparison test, okay? So sometimes you can evaluate the integral, in this case, and then you find out it's convergent. Therefore, this series is convergent. Not only convergent, moreover, we can get an estimate. Remember, right? So we can get an estimate. It's less than equal to the integral of the function plus the first term, right? The integral of the function plus the first term 2 square minus 1, right? Greater than the integral of the function. And we already evaluated the integral. It's going to be, so we are not able to evaluate, get the exact value of the series, but you still can get lower bound, upper bound. But we already know that this is going to be what? We already find the value, right? We find the value 3/4. So this is actually is 3/4. So looks like 3/4 is between those two numbers. Yeah, from above, by the above computation. Okay, but we don't need. Yeah, suppose you use the second method independent of first method, then we know it's convergent. Not only convergent, it's between these two numbers. Okay, so we are lucky we can evaluate this integral, but sometimes you are not or it's too complicated to evaluate this integral. What they can do, right? And I know this is convergent. If I just want to know whether it's convergent and don't need to estimate, we have other simple ways to do. Okay. Yeah. Before we state the general comparison test, okay. Let me look at this. Yeah, show you how do we use a comparison test to prove its convergence. Okay. So let me try. I know it's convergent. Okay. So the partial sum is increasing as m goes to infinity. So I just needed to prove it has upper bound. Okay. So upper bound means I can make the this is start from 2. Okay. So I want to get an upper bound, right? So in other words, I want to get upper bound of this term, right? So I cannot say this is less than 1/n squared because it's opposite direction. Clear, right? Yeah, because if you drop a -1, you decrease the fraction. But I really need an upper bound that looks like 1/n squared. Of course, I cannot do that. So how about I change the number, increase the number, 2 to 3 or 4. Okay, let's use a 2. Then it works. Okay, because I double the 1/n squared. Then this equality maybe holds. Okay, let's double check. This is evaluate. It's n squared less than 2, n squared minus 1, right? Let's double check. And this is going to be 2n squared minus 2. So if you move n squared to the right hand side, it's equivalent to this, right? So of course we are talking about n greater than equal to 2. Of course n squared is greater than equal to 2. So the back forward, it's important. It's not like this implies. So back forward is because, yeah, because n is greater than equal to 2, so implies n squared greater than equal to 2. Then go back to here and go back to here. Finally, you have this encode. So what does that mean? That means Sm is going to be less than or equal to 2 over n squared, right? But I know this is a convergent. Okay, this is going to be, this is a finite by the P series test. Okay, because it's finite. We know it's convergence, that's finite. Okay, I can replace n by infinity because it's increasing anyway. So this is largest possible value. Okay, so that means this partial sum has the upper bound. So therefore, okay, so that means this is a bounded from above. Okay, therefore, okay, the limit is finite, is a finite number. Okay, exists, not only exists. So that means, yeah, because first of all, SM increasing, and there's upper bound on the top. Of course, it approaches a finite number. That's good. Yeah, this comes from the limit, the section from the limit. So that implies this is a convergent. So we actually are using the so-called comparison test already. Okay, but I give all the details. How do we do the, why the, explain to you why the, you can, yeah, we will compare this series with another simple one. But this requires a good knowledge in mathematics. Looks like simple, right? 1 over n squared minus 1 less than equal to 2 over n squared. But you need some kind of knowledge in mathematics to get that point. This is a key step. Key, okay? Key step. But not everybody can work out that step. One step, right? It's a small step, it's a giant step also. Okay, so if you get that, then the rest of them is true. Okay, because you are estimate from above, because you want to prove, you guess. Okay, 1 over n squared minus looks like 1 over n squared, looks like. Okay, so it should be converted by a P-series test, but you have to get a precise estimate. Give me upper bound. Okay, if you put the 1 there, actually is great. This is actually greater than 1 over n squared. So only when you increase double it. If 2 is not good enough, 3, 4, 5. It's up to you. It doesn't matter. You can put a 100 over n squared, right? So this is argument. Okay. So you believe the following comparison test. Okay. Here's a theorem. Okay. We call it comparison test. The comparison test said that if we have n, it's positive, and it's less than or equal to Bm, okay, then n from capital M and to M, right? I just show the details here. It's going to be, okay. So this is encoded, okay, and if all the terms are negative, positive or 0, then the series is either convergent to a finite number or divergent to the infinity. So this is so you can pass M to the infinity, then you get okay. So that is enough. If the one on the right hand side is a finite, then you price the one on the left-hand side is finite. Okay, so you have two conclusions. If this is a finite, then the one on the left-hand side is finite, right? So it's convergent. Second, we also sometimes use this. If the one on the left-hand side is infinity, then the one on the right-hand side is divergent. Okay, so this is the two conclusions, but then above the encode. Okay, I did not say the one on the left must be convergent, right? Sometimes you get a lower bound. Okay. 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 So we go back to this problem here. Right? So what we do is 1 over n squared, which is n. I want to prove it's convergent. So this can be 2 over n squared, which is bn. Okay? Then you conclude that. Okay? Then you conclude that n squared minus 1 is less than or equal to. Okay? Okay. But since the one on the right hand side is finite, that implies, okay, this is a by P series test, right? Okay, then implies the one on the left side is finite. Okay, so then you conclude that. Okay, this is it's convergent. Okay. Okay, we don't know the exact value, but at least it's convergent. Okay. By the comparison test. But this comparison is a little bit difficult because you have to find the one greater than, yeah. But you have to find the one, 2 over n squared. So in fact, n squared minus 1 is less than or equal to 2 over n squared, greater than 1 over n squared. Okay. So that means this implies you have this. So if you know the value of this, then it's no 2 here. Okay, on the left hand side, just 1. So it's between these two numbers. Okay, so if you can get the value for this, then you can see that the series in the middle is between those two numbers. All right. Okay, but sometimes the comparison test is very simple, useful. For example, n equals 2 or 1, right? N over n squared plus 1, right? Please, tell me whether it's convergent or divergent, and prove your claim. Make a conjecture. Convergent or divergent? I'm not sure. Anyone? Yes. You guess it's convergence. How about you? Convergent? I want to say convergent. Convergent? What do you think? How are you? No, it's okay. They'll begin with the wet, right? It's fine. What's the few terms that matter? have no impact on the convergence of that. First few steps. Okay. I think it's damage. Okay, why? That's the reason. You see, when you look at the n, right? You know, n squared plus 1, you can ignore this lower term, right? Lower order term. So it's going to be n over n squared, which is 1 over n, right? And I know this is a divergent. We know that, right? We know, right? So the series should be divergent. But that's not that only helps you to make a conjecture, okay? But this is not a really proof. So that means the sum of this series is a infinity, right? So how do you prove that? You have to get a lower bound. So n, because when you get a lower bound, then the right hand side is infinity, then implies the left side is infinity, right? So how can I get a lower bound? If I cannot just drop a 1 there, okay? I cannot just drop a 1 there. I cannot get rid of n in the numerator because I really want to keep it very large. So, but I still can increase n to n squared. That's fine, right? Yeah, right? That's okay. You know, replace 1 by n squared. Then you get what? You get 2n squared. That's going to get 1/2 1 over n. Okay, right? That's good enough. So that's my Bn. Okay, so sigma n to infinity n is greater than sigma, right? Okay, which is going to be, and this is, I know it's infinite because this half of the harmonic series. And this is because it's half, yeah, harmonic series. It's actually a p series with p equals 1. Okay, so it's divergent. Okay, therefore we are using comparison test here. Therefore, this is a divergent. Okay, by the comparison test, let's simply write C and T. Okay. Okay, because the term on the right hand side is divergent, then term on the left hand side is greater than equal to infinity. All right, but I found out this is a little bit difficult because not everybody is good enough, you know, to find the lower bound quickly or upper bound quickly by like a replace n by n squared, because this requires a certain training in mathematics to get to that point. Looks simple, but how do I know that, right? That's the question. So there are some theories. It's not easy to get lower bound, upper bound, okay, using comparison tests. So we're going to learn limited comparison tests. Okay, later. Okay. So here the theorem called so-called the limited comparison test. That helps you. Yeah, that will be useful. Even you know this is a divergent, you know Bn. Okay. The idea is that you have two sequences. We're not going to compare A and Bn. Okay. Then I look at the limit. Okay. And here's n, here's bn. We assume that's a c. It's a limit. Okay. But that number, I assume that's greater than, it's between 0 and the infinite. Okay. Then those two series, n start from capital N, and they have the same divergence or convergence. That means both are divergent or both are convergent. Okay. Yeah, they have the same convergence or divergence. Okay. So I mean they're equivalent. If one of them is divergent, the other one is convergent. The reason is, think about the limit. Okay. The limit. Yeah, here's a proof. The proof still depends on the comparison test, because A and Bn is convergent, right? Convergent means this is a line, okay? If it's C is here, here's 0, right? And the double of C is 2C here, half of C is here, right? So if convergent means the number is very close to C. Very close to C means it's between half of C and the grid 2C. So that means it's going to be less than 2C and less than and greater than half of C. Okay, for some larger n. Okay, and for n greater than or equal to capital M. Okay, and then because that actually you get a comparison. N is less than or equal to CBN, right? Greater than or equal to half of CBN. Okay, so that means you put a you put a sigma. Okay, then it's clear. As long as you have this equality, you can see that if this is a finite, means that's a finite. If this is a finite, means this is finite. So that's why if one of them is convergent, then other ones. If this is an infinity, then I use that property. This will be infinity. Then you put this infinity. So if one of them is divergent, that's finite. If this is infinity, it implies that. So if one of them is convergent, then other one is convergent, because we have this in code. Okay. Okay. Now, if you use this, it will be much simpler, because we don't need to repeat the same arguments over and over again. Let's go back to this problem. Okay. This is a problem. It starts from 1 n squared plus 1, right? So your n is going to be this. Okay. It's hard for me to get an upper bound and lower bound, but I can easily see whether it's convergent or divergent because I drop unnecessary terms, right? So this is my Bn. It's 1 of n, which is Bn. Then it's harder to tell whether n is less than or equal to Bn or greater than or equal to Bn. I know it's less than or equal to Bn, but can I get n greater than or equal to half of Bn, right? Because if it's less than or equal to Bn, it's not enough to prove the series convergent, divergent. Okay, I know n is less than or equal to Bn, but the series on the right hand side is infinity does not mean the series on the left hand side is infinity. Okay, it's useless. Okay, you have to get a lower bound for n, which is challenging to some students. So it's better just use the limit comparison, because you can quickly figure out the Bn. Then you take the limit as n approaches infinity, an Bn, okay, which is going to be n Bm is going to be I think it's going to be n over n squared plus 1 divided by 1 over n, right? And after you simplify, you get n squared over n squared plus 1. The answer is what? Okay. So the limit is just equal 1. It's a positive number. So then both have the same convergence or divergence. Since this is a divergent, okay, which because this is a harmonic series. Then this is also divergent. Okay, by the limited comparison test. Okay, simply just call right LCT. The comparison test, the limited comparison is slightly different. Okay, for comparison test, if you want to compare two guys, right? Right? If you want to prove someone is bad, someone is good, right? And you can say, oh, this guy is worse than the other guy, but the other guy is already a criminal. Right? So that's comparison, you know. Okay, but limited is just slightly different. Just say it's a limited case. Is that when time goes to infinity, right? If their behaviors are getting close, similar, and the other guy's bad, his friends also is good, bad guy. Okay. So this is a limited comparison test, and sometimes save you computation. You don't need to learn lots of tricks to estimate. Okay, you still can conclude using one of them to conclude the other one. Okay, and the argument is already given here. You don't need to repeat that over again. Okay. All right. So here's another problem. We did it before. Okay. Now, if you use a comparison test, it's a little bit challenging because you have to compare with a very good series, P series. Okay. But if you use a limited comparison test, it will be much easier. Okay, this is n, right? If you drop -1, so you get bn, which is just 1 over n squared. And yeah, bn and are almost the same for n sufficient large, right? So clearly, I just simply, if the procedure is like that, just drop the constant terms, then the limit is always equal to 1. Okay, it's always equal to 1. Don't worry about that. Most of the case. Okay. So and we know Bn is convergent. Why? You have to say by the P-series test. Okay, because P equals 2, which is greater than 1. I have to indicate that. Okay. So we simplify n, we get a Bn. But the Bn, it's obvious it's convergent, the sigma B. So the sigma n is also convergent. Okay, by the comparison, limited comparison test. This implies is convergent by the limited comparison test. So a complete solution involves several steps. You cannot just simply write convergent or divergent. You have to prove that. When you prove that, you have to measure which one you're talking about, right? You find you find a simplified sequence. Okay, use that sequence. You can easily, for that sequence, you can easily tell the corresponding series is convergent or divergent. Okay, then you also have to prove that this new sequence is very similar to the original sequence because the limit is going to be 1. Okay, and then by the limited comparison test, you can prove that the original series is convergent. Now, why is this convergent? If we without making this, by the limited comparison test, you have to give a proof. The same proof we did for the limited comparison test. Okay? So you have to mention that. Either you quote that part, you don't need to repeat the same procedure. Just like when you write the program, computer program, right? You can write this blocks and just quote, put it here, right? Quote that. Otherwise, you have to repeat the type of the same, like a half page, for that program, and it's too long, right? Yeah. So the same thing here. Limited comparison test represents that argument, the proof we did for the limited comparison test. So you see, I mentioned limited comparison test. I give a proof, but you don't need to repeat that for every individual problems. When you find a simple series, okay, and you believe that you can use that to check to tell whether the original series is convergent or divergent, right? But you have to repeat the same idea over and over again to do comparison. Actually, essentially, it's comparison here. So all you have to do is just quote, okay, limited comparison test. Why you can use the limited comparison test? Because the limit of this quotient is going to be a positive finite number. In many cases, just equal to 1. Okay. Yeah, I remember a long time ago, I this was a very interesting program. So I said, okay, I'm going to borrow a C+ for Java. And when I started learning programming for fun, just for fun, not for something. And I find out, yeah, you can write a blocks. You can use the over again, okay? You don't need to repeatedly type the same thing over and over again. Okay, that's simplifying their programs. Yeah. All right. Yeah, I write the program for my kids to do the math, addition, multiplication on the computer. And he tries 3 times, still failed, and the sentence shows up, ask your daddy. Because if you purchase from a market, you don't see, personalized, same language shows up. Okay. So one day I get a phone call from my daughter saying, Daddy, I want to get a bachelor degree in mathematics. Do you mind? So I said, should I make any contribution like money or tuition? That's very important. And he said, well, you just need to pay me 1 more course. It's okay, that's all fine. So she got a degree, 2nd degree in mathematics. Yeah, the original degree is in microbiology. All right, so let's do the next problem. Okay, so let's look at this n over n cubed plus, okay? Do your best. First, make a conjecture. Then try to prove your claim using any of the methods you so far used. You have learned comparison test, a limited comparison, integral test, and so on. Okay. Yeah, first of all, based on what you learned, when you make a quick jump.
All right, so this is a convergent. The reason it's convergent is if you ignore the +1 in the denominator, right? Drop this, then you simplify it, right? And you will get 1 over n squared, which is Bn, right? So Bn, sigma Bn is convergent. Why? Because it's P-series test. Okay. So sigma, first of all, let's do this, right? It's going to be Bn. This is convergent. I just simply let you less than equal because there's only two options, either finite or infinity. Okay, always, yeah. By the P-series test. Okay. By the P-series test. And now what? You have two options. One is use the limit comparison test, okay, to prove sigma n is convergent. So you take the limit, okay, and that is going to be actually is going to be 1. I always tell you, if you just drop some constants, the limit is always going to be 1, okay, because no bigger change, right? But if you really want to prove that it's okay, it's going to be like n over n cubed plus 1 over n squared. After you simplify it, you will get n cubed over n cubed plus 1, then divide the numerator by n cubed, right? Then it's going to be, so that's going to be 1 plus, that's 1, right? I told you it's guaranteed, it's always 1. Okay. Then you jump to the conclusion, this is the convergent. Why? You have to say that by the limit comparison test. You don't need to repeat the whole argument because it's already proved that, right, for limit comparison test. So you just say more precisely by the idea we use that to prove the limit comparison test. We apply the idea to here, you can repeat the same procedure to prove this is convergent. But that's one option. Another option is when I look at this, this is convergent anyway, but it's easy to see that because it's +1. So I can easily drop a negative and enlarge this is a Bn, right? Which is going to be, 1 over n, right? So comparison test is also works where you don't only take the limit. Okay, so that implies this is a finite. Okay, so therefore it is convergent by the limit comparison test. By the comparison test. Okay, not necessary to be limit comparison. You can have a direct comparison. Okay, there's no need to the limit comparison test. Okay. Now let's look at the strange one. How about 1 over n to the nth power?
Is it convergent? What I mean, and how to prove it? Right. This is clearly it's convergent. Why it's clearly? Because in squares already make it convergent, right? So at least for n greater than or equal to, because this n is less than or equal to n squared, 1 of n squared, because n is large, right? So which is bn? That's enough. Okay. So I just use a comparison. I don't use a limit comparison. I use a comparison test. Okay. Then n start from 2. This is a convergent. Why it's convergent? By the P series test. Okay. And you have to say that P equals 2. And this implies this is a convergent by the comparison test. Can you use a limited comparison test? In somewhere, but cannot prove it directly because your limit is going to be 0, not a non-zero number. So the convergence, yeah, you have to modify the limited comparison test to do that. So the comparison test is the best choice. Okay. How about this? Ooh. Right. Well, I know sine x is almost equal to x as x approaches 0. I know that. Why? Because the limit is going to be 1. So basically, when x is small, sine x is almost equal to x. Okay, that's good enough. So if n is a sine 1 over n squared, my bm is just 1 over n squared. Okay, so if you look at the limit n over bn, this is just a limit sine 1 over n squared, 1 over n squared, and this can be replaced. This is going to be 1 anyway. It's obvious because 1 over n squared. All right. So you can use a limited comparison test. Okay, since this is a finite, okay, because by the P series test, okay, we conclude that okay, so n start from 1 to infinity, okay, by the limited comparison test. We need a so whatever you said that should be in logic, right? There's a reason, then the conclusion. That's it. Okay, and sometimes you do need to quote the test, right? Comparison test, limited comparison, or integral test. Okay, then this is called a complete solution. Okay, so in this chapter, Okay, you don't get full credit for the so-called correct answer, because the answer itself should be the whole solution. It's not like a convergent type, because convergence is easy. You just look at the next, someone sits next to you. As you see convergence, you can copy that word quickly. Okay, I do that. Somebody the rotate their eyeballs when sitting there, I can see that. Okay, even you don't need that. You don't need to turn your head, but only you can copy is use a divergent convergence, and then you have to make sure the guy sitting next to you really good, better than you. Otherwise, otherwise you copy the wrong. Okay. Ah. Right. So next. All right. I think this one. How many different ways to prove it's divergent? It's divergent. When I see this series, I know it's divergent. Okay. I use one of the methods. I'm going to see immediately it's divergent. Okay. So you think about it. We still have a few minutes. We have 15 minutes. So I give you 1 minute to write down all the possible ideas to prove this divergent. Yeah, when you do the homework, try to write down all the possible solutions, not just only one. Okay, it's hard to find the solutions at the end of the book, I guess. Answer key. Yeah. There's no answer key to homework problems. Okay. Yeah, you go through all the possible tests, can try one by one. Okay, gradually you are going to build up some experience, so you know how to do it. Okay. Prepare for this chapter. My suggestion, that's what I did when I was a student. I write down each of the tests on a piece of paper, summarize it, otherwise have. And for each problem, I put a typical example. Okay? Okay, that's example, can use that method to do it. And also you note this example can be also used as a test. So, okay? Then, so when you prepare, then, you look at it very clear. Otherwise, you have to go through all the pages. Okay? You needed to learn how to summarize what you learned, especially in the college. It's different from high school. Yeah, in college, you learn lots of stuff every day. So it's harder to digest. But don't summarize everything, put on a cell phone. And don't take cell phone out during the quizzes test. Last time when I walked here, I saw the cell phone on the lap. Okay, I just stay off. Yeah, you can pay attention, right? I actually take a picture. It's recorded. It's easy to see through that. You see, because the table is not that wide enough to cover all the movements of the hands under the table. I can easily see that if you stand here. Yeah, last time I just take a picture. And I sent the picture to the student by email. So I told him You got 0 on that quiz. That's the first warning. Okay, and here's the evidence to prove that. And he was surprised that I took a picture. All right, so, but yeah, you needed to learn how to summarize the, write down all the tests on piece of paper, okay, and then put a typical example, okay, your favorite examples. Okay, so when you look at this problem, okay, let's try all the possible ways to do. I look at the A, okay, and I know this convergent to 0. Okay, so I cannot use the divergence for test to prove it's divergent. Okay, so the divergence inconclusive, right? Using the divergence test for divergence. So I cannot use that to prove it's convergent. I cannot use that to prove it's divergent. Okay, so divergent test, the test for divergence does not work. Then what is the next one? The next one, direct computation. No, I cannot summarize, right? The partial sum, I cannot group them into one fraction. No, it's impossible, okay? So I give up that. Origin definition does not work. For the convergence, you have to look at the partial sum and take a limit. And I cannot can put all the terms into one, okay? I cannot get rid of sigma, that's the key point. So the partial sum, it's not working. So let me list all of them, right? So the first one, we learned that the partial sum. So we don't know how to, whether it's convergent or not, that does not work. Second, right? And I know, okay, this convergent 0, but it's inconclusive because if it's not convergent 0, then I can say it's divergent, okay? If it's convergent 0, because that is not necessary, not sufficient condition, okay, for convergence. So inconclusive is I cannot, convergent or divergent, I cannot say. Convergent or divergent, right? I don't know. But the sequence is convergent. There's a series. I don't know. So what is next section? Integral test, all right? Right? We try. Integral test, one by one. Integral test, f of x equals natural log of x of x. I have to verify it's positive. I think it's positive, okay? F of x is positive if x is greater than 1. That's enough. Natural log of x is greater than positive when x is greater than 1. But the second, you have to find the derivative because decreasing is important. It's required. So it's 1 of x times x minus 1 times natural log of x. Right? Just use a quotient rule to find the derivative. Right? Okay. So it's going to be 1 minus natural log of x squared. When this is going to be negative, I think when if x is greater than e, okay? If x is greater than e, that's okay. As long as x is large enough, then it's negative, it's decreasing. Okay, this implies this is a decreasing on e and the infinity, right? E is just only 2.78. So we are okay using the integral test. Then you can say that we can use the integral test after you verify these two conditions. All right, so look at the integral. Integral, this is start from 1 to infinity, right? And are we able to evaluate integral? Because I know I can evaluate integral. That's why I spend so much time to try to prove the conditions required, in the integral test. How can I evaluate this integral? Well, use a substitution. Okay, so this is going to be the limit b approaches infinity. It's from 1 to b of this integral, and I just write down the antiderivative. Okay. you can do that. Natural log, I think it's natural log of x. And we did that problem in the last section. Okay, so when you differentiate natural log and natural log x, then you get natural log of x. Hold on. I made a mistake. Okay. Natural, no. Okay, so we have to find the antiderivative of this. Okay, so let's do it. So we have to find the antiderivative. Okay. So I use a substitution. Okay, then you will get, it's u, right? I think it's just u, that's all. So actually it's half of u squared plus c. So it's half of natural log of x plus c. Okay, that's the antiderivative. Okay, my memory is wrong. Actually, yeah, this is the antiderivative. So I put that. So that means the integral from 1 to b is going to be half of natural log of b squared minus, okay, which clearly approaches infinity, right? As b approaches infinity. Okay, so it's divergent. I know it's divergent. Okay, so that concludes, that implies it's divergent. Okay, but you have to say by integral test. Okay, by the integral test. So we try to go through all the possible tests whether we can use it. Okay. Okay. So some problems you can use all these tests to prove. Okay. Some series there can only one special test. Okay. So 1, 2, 3, 4, right? 3 integral test works. 4 comparison test or limited comparison test, right? So I know it's divergent, so it's going to be natural log of n over n. But when I look at this natural log of n over n, this numerator is getting larger. Even without anything in the numerator, just 1, it's already divergent, right? The p-series test. So clearly, this goes to infinity, right? On the top. So definitely it's greater than or equal to 1 over n. Okay? It's bn. So when? For what's larger n? Natural log of n is greater than or equal to n as long as this is greater than or equal to e. Okay? Yeah, because natural log of x is greater than 1 if and only if x is greater than or equal to e. Okay? Yeah. So when n is large, really large, then it's greater than n. And clearly, bn is divergent. You know, the power geometry series. This is a harmonic series. Okay. So since this is, let's start from 2 or from 3, doesn't matter. This is the infinite, okay, by the p-series test, okay, and p is going to be 1. Or you can also simply say harmonic series, okay. So this conclude that, okay, this is divergent, okay, by the comparison test. Can you use a limited comparison test? Probably not, because the limit should be equal to a finite positive number, unless you use a modified version. So we're not going to use it. Yeah. Let's look at the modified. I don't have a time here. Yeah. So this is a modified version. Is as follows. Modified version. So if you have n greater than or equal to bn, no. Yeah, you cannot say greater than or equal. There are 2 possible cases. Okay. There are 2 possible cases. N greater than 0, bn greater than 0. So the limit could be n over bn equals c, still c. There are 2 possible cases. If you see 0, what happens? What you can get? if C0 is n is very smaller than Bn. Okay, so that means n of a Bn is really less than equal to any small number. So any small number is just less than 1 for n greater than n, right? So that means, okay, so that means if Bn is divergent, then n is divergent. This, you only have this inequality. You don't have the two sides inequality. Then you decide which one. You put a sigma on the top. All right, you can still use that. So if one side is the right hand side is finite, it implies left hand side is finite. Okay, but if C is infinite, okay, if C is infinite, that means for sufficient large n, it goes to infinity. So then this is going to be greater than or equal to 1. All I need is just greater than or equal to n. So you have this inequality. Okay. So then you have a then you decide, which, yeah, then you only have this inequality. Not like an original limited comparison test. You have two inequalities. Okay, there's only one. Okay, so if this is infinite, and you call that. This is infinite. This is finite. They call that. But that do not have a equivalent convergence. Okay, I cannot say this is a convergent that one. Okay, so we will look at this later. Okay, stop here today.